Infrastructure as Code, or IaC, represents one of the most transformative shifts in modern cloud governance. Instead of configuring systems manually through consoles or scripts, organizations now define infrastructure using declarative templates that can be versioned, tested, and deployed automatically. Within SOC 2 programs, IaC governance ensures that every deployed configuration aligns with approved security baselines before reaching production. Guardrails and policy as code frameworks bring automation to compliance itself, embedding rules directly into the deployment pipeline to prevent violations before they occur. This approach strengthens CC8, change management, and CC7, operational monitoring controls, by guaranteeing that every environment is provisioned consistently, traceably, and securely. The control objectives of IaC governance center on standardization and traceability. Automated provisioning eliminates the human error that often introduces drift and misconfiguration. Each environment is built from the same template, ensuring consistent application of encryption, logging, network segmentation, and access rules. Because the entire configuration is stored as code, changes are automatically documented and auditable. Compliance checks become part of the deployment process rather than post-deployment audits. These objectives directly support SOC 2's emphasis on control repeatability, providing proof that configurations are not one-time setups, but continuously governed through policy enforcement and evidence generation. Service Control Policies, SCPs, extend governance one layer deeper for AWS multi-account environments. SCPs operate at the organization level, defining universal restrictions that even administrators cannot override. They can block disallowed services, restrict geographic regions, and enforce organization-wide tagging requirements. Each policy violation should generate a log entry for evidence and be reviewed periodically to ensure relevance as AWS releases new services. Properly managed SCPs form an immutable compliance perimeter, protecting against inadvertent or unauthorized changes that could weaken controls. Their annual review cadence ensures they evolve in tandem with cloud service expansion and internal risk appetite. Pre-deployment validation is the operational heart of IaC compliance. Every infrastructure change should pass a policy check before promotion to staging or production environments. Pipelines automatically evaluate templates, block non-compliant changes, and provide developers with immediate feedback. Failed checks generate actionable remediation guidance, reducing time to fix while improving long-term compliance literacy. Each evaluation produces logs and reports which must be stored as audit evidence. This preemptive enforcement model satisfies SOC 2's change management requirements by proving that risky configurations never reach deployment, effectively demonstrating control operation through prevention rather than post-incident correction. Even with perfect templates, configuration drift remains a persistent risk. Drift occurs when resources in the live environment diverge from the defined IaC standard, often due to manual adjustments or unsynchronized updates. Continuous drift detection tools monitor these discrepancies, flagging unauthorized changes and triggering automated remediation or alerts. For instance, if an S3 bucket becomes public when it should not, the system can immediately revert the setting or open a ticket for review. Each incident should be logged, investigated, and closed with documented resolution. These drift reports demonstrate operational vigilance, aligning directly with SOC 2 CC7 monitoring expectations. Evidence generation underpins audit readiness for any IaC program. Every policy evaluation, compliance scan, and deployment event should produce logs that are time-stamped, hashed, and archived. Maintaining hashes and metadata for IaC files provides proof of file integrity and historical traceability. Change tickets linked to policy results illustrate how deviations were identified, approved, or remediated. Aggregating this evidence into reports or dashboards allows auditors to see the full life cycle from change request to enforcement and validation. Automated evidence collection not only reduces administrative burden, but also ensures accuracy, continuity, and completeness across audit periods. Access control and approval workflows ensure that policy as code systems remain secure and trustworthy. Only authorized developers should propose or edit policies, and each modification must undergo peer review. Segregation of duties prevents a single individual from both authoring and approving a policy that governs compliance outcomes. Every approval and merge action should be logged within the repository, accompanied by automated policy testing before integration. This combination of human oversight and automated validation ensures that policy frameworks themselves maintain their integrity as auditable controls, a principle that resonates directly with SOC 2's governance and change management requirements. Applying these guardrails consistently across multiple cloud providers extends SOC 2 governance into a true multi-cloud environment. Unified policy templates can cover shared requirements such as encryption, tagging, and IAM boundaries, while provider-specific exceptions handle platform differences. Testing should confirm that identical security baselines deploy correctly on AWS, Azure, and GCP. The resulting evidence policy, evaluations, remediation logs, and CI/CD results must align across providers for audit parity. This cross-cloud harmonization demonstrates not only control operation, but also organizational maturity in managing compliance at scale across diverse infrastructures. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Metrics and Key Risk Indicators, KRIs, translate the health of your IaC and Policy as Code program into measurable performance. Track the percentage of IaC changes that pass validation on the first attempt, an indicator of developer alignment with security standards. Measure the number of policy violations detected per month, categorized by severity to identify systemic weaknesses in configuration practices. Monitor the average remediation time for non-compliance to evaluate responsiveness, and calculate the policy coverage ratio across domains such as IAM, networking, and encryption. These metrics, when reviewed regularly, prove that guardrails aren't theoretical. They're actively preventing, detecting, and correcting issues. They also supply auditors with quantitative assurance that IaC controls operate continuously throughout the year. Tooling integration connects policy enforcement to the broader compliance ecosystem. Open Policy Agent, OPA, and conftest can integrate seamlessly with Terraform, Kubernetes, or container pipelines, evaluating infrastructure definitions during pull requests or pre-deployment stages. Centralized dashboards in a governance, risk, and compliance (GRC) tool display aggregated policy results, offering leadership a unified view of control health. Real-time alerts on policy failures keep engineers informed while generating immutable logs for audit review. These integrations link engineering automation directly with SOC 2 evidence expectations, converting operational signals into compliance artifacts automatically. Versioning and change management for policies ensure that governance evolves in a controlled, auditable manner. Each policy release should be tagged with a semantic version, reflecting whether changes are minor, major, or corrective. Pull request approvals serve as checkpoints where reviewers validate both rule accuracy and business alignment. A changelog documenting added, removed, or modified rules provides traceability for auditors seeking to understand when and why policy criteria changed. If a new rule inadvertently blocks valid configurations, rollback procedures must be documented and testable. This disciplined version control approach mirrors software engineering best practices, reinforcing that compliance rules themselves are living code, requiring governance parity with application development. Testing and quality assurance prove that policy as code performs reliably before production enforcement. Unit and integration tests should verify that each rule detects violations correctly and doesn't generate excessive false positives. Negative testing, where intentionally non-compliant templates are submitted, confirms that the guardrail blocks changes as intended. Reviewing false positives improves developer trust, ensuring that policies remain precise rather than obstructive. Recording QA results, including test scripts and screenshots, supplies auditors with objective proof that policies function as controls rather than static documentation. Effective QA keeps governance credible and avoids the pitfall of over-secured pipelines that slow delivery without measurable gain. Incident management for IaC failures ties automation directly into the organization's response framework. When a deployment fails because a guardrail blocks a non-compliant configuration, the event should automatically generate an incident ticket. The record should describe the failure, the affected resource, and the remediation steps taken. After resolution, teams should review whether the policy needs refinement or if developer education is required to prevent recurrence. Capturing these tickets and their closure notes provides concrete evidence of monitoring, response, and continuous improvement, elements central to SOC 2's CC7 operational criteria. Every block deployment becomes both a control test and a learning opportunity. Governance and oversight give structure and accountability to the policy as code program. A formal policy review board, typically composed of security architects, DevOps leads, and compliance officers, should meet quarterly to evaluate rules, discuss exceptions, and approve updates. Reports summarizing violations, remediation statistics, and improvement initiatives should feed into broader risk governance sessions. Meeting minutes, approval logs, and attendance records all serve as audit evidence of oversight. This governance rhythm ensures that IaC policies don't stagnate but evolve alongside infrastructure, threat landscapes, and compliance frameworks, embodying the governance in motion principle that SOC 2 auditors look for in mature programs. Cross-framework alignment enhances the value of IaC evidence across multiple standards. Many guardrail rules correspond directly to CIS benchmarks, NIST SP 853, or ISO 27001 Annex A controls. Mapping each rule to these references allows teams to reuse the same evidence for different audits, reducing duplication and increasing assurance consistency. For example, a Terraform policy that enforces encryption at rest may satisfy both SOC 2 confidentiality and NIST control SC 28. Centralizing these mappings in the compliance repository creates a transparent crosswalk that auditors and customers alike can trace, proving that the organization's cloud governance is grounded in recognized best practices. Training and enablement keep policy as code effective by ensuring developers understand both the tools and their purpose. Educational programs should cover how OPA and contest evaluations work, how to interpret policy failure messages, and how to write compliant code. Providing sample templates and sandbox environments encourages experimentation without production risk. Annual certification for IaC contributors reinforces accountability, while logged completion records provide auditors with evidence of ongoing competency. Empowered developers write cleaner code, require fewer remediation cycles, and transform governance from a gatekeeper into an enabler of secure, compliant delivery. Automation maturity evolves in predictable stages. Early programs rely on manual policy checks before deployment. As automation matures, CI/CD integrations enforce policies automatically and generate real-time feedback. Continuous monitoring tools then extend enforcement into runtime, detecting drift and triggering remediation without human input. The final stage introduces predictive analytics, leveraging historical data to forecast compliance risks and suggest policy optimizations proactively. This evolution reflects SOC 2's broader goal of continuous improvement, moving from static compliance verification to dynamic, self-correcting governance systems. Even robust IaC programs can falter through common pitfalls. Untested policy updates may inadvertently block critical deployments, halting pipelines and frustrating teams. Inconsistent guardrail implementations between departments create uneven protection and audit confusion. A lack of detailed logging obscures evidence trails when auditors request proof of enforcement. Correcting these issues requires standardized QA procedures, centralized policy repositories, and mandatory log retention. Uniformity and transparency converts IaC from a developer convenience into a verifiable control system. Metrics review cadence ensures governance stays responsive. Monthly reviews should focus on violation trends and their root causes, while quarterly sessions assess policy coverage and efficacy. Annual comparisons against external benchmarks validate continued alignment with best practices. Summarizing these insights for leadership closes the loop between technical operations and executive oversight. The ability to demonstrate not just compliance, but the measurement and refinement of that compliance defines mature IaC governance under SOC 2. Auditors evaluating IaC guardrails expect specific forms of proof. Policy files and rule definitions show intent. Evaluation logs and QA reports confirm operation. Incident tickets and approval records demonstrate governance in action. Change logs and review board minutes capture accountability, while dashboard exports visualize continuous compliance performance. Together, these artifacts portray a full life cycle, from policy creation and enforcement to validation and improvement, meeting SOC 2's evidence expectations for completeness and traceability. Maturity in IaC governance follows a natural progression, starting with documented standards, advancing to enforced guardrails, evolving into automated evidence collection, and culminating in unified multi-cloud policy governance. At full maturity, compliance operates as code, continuously validated, automatically recorded, and transparently auditable. The result is a living control environment where assurance is built into every deployment, not added afterward. In essence, infrastructure management becomes a measurable, self-governing system that demonstrates continuous SOC 2 alignment in real time. In conclusion, IaC guardrails and policy as code transform compliance from a reactive activity into a proactive, automated safeguard. They ensure every resource meets defined security and privacy expectations before it ever touches production. With automation, governance, and evidence integrated into pipelines, organizations achieve consistency across clouds and teams. The result is not only faster, safer deployments, but also stronger, more defensible audit outcomes. This continuous compliance model sets the stage for the next discipline in operational assurance: penetration testing, findings management, and remediation proof as the closing link in the control validation chain.